My favorite thing is to play with SIR models, and I will not defend all the bad things people said about them before, but today I'm not really going to talk about SIR models. I'm going to talk about clustering of age groups in infectious disease, and what you see in the first graph is just the time from the beginning of the pandemic. So, whoops, sorry, pointer. So you see this was our first wave, second wave, third wave, fourth wave, Omicron, and then it had a few bleeps. And I want to try and look how the age structure of the disease changed in time. So just to show you, so this is an example from the UK. So you can see that if this would be some scale of, let's say, cases per 100,000. I don't remember what it actually is, and different age groups at the different colors. You see that the pattern is very different between the ages. This is the same thing with people who got to intensive care. But as you see here, the ages were clustered in all kinds of different ways. So look here in 4 years, here a group of about 10 years, here a group of 20 years. And so the question we were asking ourselves way before COVID is can you find data-driven ways to decide how to cluster these age groups? And my main motivation, because I was obsessed, I guess, for about 10 years, to try and estimate these matrices, who, for SIR models, is how many people infect how many people at different ages. So if we take, for example, this is how many, let's say how many people at the age 0 to 4 infect people at 0 and 4. And this is how many 0 and 4 infect 35 to 39. Usually you have the diagonal that is usually where most people meet most people at their same age. But for example, like here, so this is parents meeting children and children meeting parents. Okay, so you want to try and see if you can estimate such matrices. And usually you're given a matrix like that, but this has 256 entries. So how the hell are we going to parameterize such a monster? Yes, please.
Usually these matrices are symmetric. This is not symmetric because it is easier to infect a larger age or something?
So you could come up with them in several different ways. And I'm going to show you a data-driven way of doing such a thing. Okay? So that's exactly what I'm trying to see. Can data tell us? How can we decide what are these entries into the matrix? Okay? And as people before me, they showed that these things could really change with time. So school closing, right? So kids won't meet other kids. Holidays, changes, weather, and so on. So we really want to see if we can try and see how this interactions change with time. And because I have only 15 minutes, I'm not going to go deeply into the model, but you could think of the simplest statistical model. So the number of infectious that you're trying to estimate is the true number of infectious in the population, plus some noise term that's normally distributed with a zero mean and some variance. Okay? And if I have two time series, so let's say age 5 versus 6, I want to see if they're similar. Okay, that's kind of the question. If they're similar, I'll cluster them together. If they're different, and I'll show you, you have to develop a measure for that, I decided they're a different group. Okay? So what I'm going to show you is an algorithm that's based on a divisive top-down hierarchical clustering approach. Okay, initially, all the incidence data clustered together in one cluster, which will be my root node. So I'll take the entire population. I'll look where is the first division that I should divide the population. Therefore, where is the biggest difference? And then at each step of the algorithm, I'll examine if this division is statistically significant. And if it is, then I'll go and do the next partitioning, okay? And this is done in an iterative way, and when my algorithm gets to its stopping criteria, that's how I stop dividing my population. And this is just, if you look, so if I had this population, this is the entire population. At the end, I decided to divide it to two groups here, to 0 and 13, and then 14 and the rest and above, okay? And the way it was, I had one big population. I found the first division, which was here, 0 and 13, the next, and 13 above, okay? And then I tried to do another division, and if in this case, no other divisions were statistically significant, so I end up with two groups. But if I had other ones, and I'll show you soon that we had other ones, then this population could be further divided. Okay. And so since both the deciding the location and the partitioning and whether or not to perform the partitions are based on the same criterion, okay, and I'll show you in a second the criterion, it is critical that each of these steps will be performed using different incidence data, representing observations of the same process, okay? So I don't want the same data, I don't want to overfit, so therefore I want to split my data into two. So what I can do is I can take my time series and randomly divided it to two different time series, or what we did in this case, we looked at each 2 years, let's say kids 5 to 7, so 5 to 6 is one group, and 6 to 7 is another group. And therefore, that's a way that you could do this two-step process, okay? And here we assume that the groups, okay, that's what I just told you, just the example. And I can estimate the variance of these two time series, which is very important. And I use the first set of data to do the first division. And then the second set of data, I use it in order to make my criteria. I just want to point out that we can do something a little bit more fancy, and we can say that the data could be the same up to a constant. So if we suspect that one age group has a different reporting rate for some reason, so I can just multiply it by this constant, and I have to estimate it in a different way. And so when I say similar, again, I have two meanings, having the same rate, or what I said is the same shape, so it's up to this factor, okay? And then you come up with this matrix that it's not so important, and again, we don't have time. And then we just look at what maximizes the distance between these two groups, okay? And then with the second set, what I use this statistics and the chi-square test is to test your null hypothesis, and then you know if to partition or not. Okay, and because we can do this many times, so we have to worry about the family error rate, and we have to fix this alpha and check and do a fixing using multiple testing, okay? And so you have to take into account this, and then you can develop a pseudocode that does it, and just to show you that you could do it. And now just to show you an example, so this is influenza from, I think, 1998 in Israel, And you can see these are all the age groups, and the algorithm found that you could divide this year into two groups, 0 to 13 and 14 plus, and then you could create this time series, and they're different. Okay, so this is the idea of how the algorithm works. And now we'll go through the 5 waves of the pandemic. So in the first wave, we saw clustering of up to 20, which is the red line, and 20 and above. And we think that part of why we saw this is, first, we had this lockdown, and second of all, the age 20 and above were the people who traveled, so probably they brought it in and mixed more between themselves. Okay? In the second wave, that you see, first of all, they're much closer. Okay? And the division was different. It was 0 to 60 and 60 plus. So apparently, the people 60 at plus, at that stage, we knew that there are people at risk of being hospitalized and dying, so they probably were more careful. Okay, and now you see it got more interesting with time. So in the third wave, we had a division of 2, 4, 6, 1, 2, 3, 4, 5, 6 groups. And you see that they're very different. In the fourth wave, we even had more groups. And in the fourth wave, you could see, for example, all kinds of, also in the third wave, but less because the vaccination came very late. But in the fourth wave, you could really see how vaccination played and had an effect. And again, in Omicron, you could see, again, the 60 plus were much lower. It still finds 4 clusters. But you could think that the first 3 clusters are very close. One thing I forgot to mention, one thing our clustering does, it keeps groups that are in sequential age together. Okay, so it cannot make any cluster in the data. So it always looks at ages that, so you cannot have a cluster of kids 5 and people 50. Okay, so it has the sequentialness, which is something we want to use. This final graph shows you the same thing, but we divided the population into 3 groups. One is the general population, okay, which is this top one. The second row is the ultra-Orthodox, and the third group is the Arabs. And you could see how it differs between the 5 waves, and you could speculate why, and so on. So do I have more time? Okay, so maybe questions? I can show you the conclusions, but maybe better to take questions.
Can you take your results and use it for vaccination policy, mostly your results about the age? Can you prioritize the number of vaccination?
Okay, so that was exactly the original motivation, because we need this matrix to know who to vaccinate.
Yes.
Okay, so the idea when we thought about developing this in pre-COVID times was to see from the data what are the age groups that are important, and because people usually do it in an ad hoc way, so they can do just every 10 years, every 5 years, or decide people 0 to 20, and so on. And the idea here was exactly to do it data-driven in order to plug it into the SIR models and look at optimal vaccination policies, or at non-pharmaceutical interventions and see where, like, if you have these entries, you know where are most of the contacts, so you know where to intervene. Okay, that was exactly our motivation.
I see, but do you like in your research center, do you take into account not just like the infectious rates, but you take also the side effects of the vaccination? And do you take like holistic picture like of
so you can do once you have a model, then you could, you know, put all kinds of constraints into it. That's the relatively easy part. To come up with, I won't say a good, but a reasonable model, that at least from my science hat, that's the hard part.
So you said that the result of your work is actually constraints that can be applied in the SIR model or another model?
Yeah. So the idea is, so this was my original motivation, but you could think of, that could show you all kinds of other things. So if you know, if we go again to look at this, so if you want to think of interventions in the Orthodox, they might be very different than the Arabs and the secular Jewish population. Okay, so that's exactly the idea, to try and understand the age structure dynamics and then think how you can reduce the disease. So thank you.